So, back from the break, and we are talking now about a change of abstraction. So this is about key points, because when you do this analysis that we have done until now, you always look at the whole image, and the whole image can be time consuming to analyze. And therefore we go to something called feature points, which are very distinct points, mostly marked up around near corners in the data. And here we can see an example, a very basic example actually. You have a checkerboard where we want to identify the corners, and there are a lot of different ways of doing it, but a popular one is the Harris corner detector. And that one is a kind of a filter based on the structure tensor. So that's essentially a tensor based on the derivatives in different directions. And let's see, if we just put a threshold on these to just identify which ones are the relevant ones and plot them together with the original image, we can see here that, okay, we got very nice dots here at every corner. Maybe too many, but anyway, there are characteristic points at each corner. And if we look at that on the real data, we have this, again, this filtered bone slice. And if we apply this corner detection using the Harris detector, we can see here that we have a lot of small dots all over the image. And if we plot the threshold dots, we can see that they actually land pretty nicely on corners in these features here. This one may look a little bit strange, but the reason that you have a dot in the middle is that there is actually a little bright dot in the middle here. So that is the reason why we got also a corner point here. A pretty strong one, apparently. So these can then be used in order to do the tracking. And this reduces our tracking efforts, because we don't have to do any labeling anymore. We don't have to compute any region properties, because these corner points, they are really bound to the shape of the objects. So you can see that they are quite stable and also fixed on the features. And you can see here in this example, I'm going to skew and translate and rotate this image. And you can see here how these properties actually still follow the corners of this checkerboard. So this is a good thing. Still, you can see that there are many points, and that may have to be filtered out by pruning, saying, okay, some of these points, they are not really, there can't be so many corners in this little area. So with the help of maybe some opening and closing before you do the thresholding of the corner map, you can probably reduce these points further. So that would also make it more clear when you do tracking. Otherwise, it will probably be a little bit confusing to find the right spots. Another thing is, in the previous slide, we only identify we have a corner point, but not really which one is what. And what you can do is actually to add descriptors. Each corner point gets a unique description, which is very often a binary number with, well, 128 to 512 bits. So it's a pretty large number. And it's based on the neighborhood around the point, and also different blurred version of the neighborhood, and that gives us some kind of bit chain. In this case, I'm only showing the first 25 out of 256 bit flips for the 9 corner points or 10 points, and you can see they are located on different places in here. And every point is, as you can see, also very unique, and that makes it possible actually to do direct lookup tables from to map features in one image, in one frame to the next frame. These should also be, actually I didn't check that, these should also be rotation invariant, rotation translation invariant to be really useful. Otherwise it doesn't make so much sense. So let's go on. This is just a function used to show differences. So let's create some data. We have here the original and one that is moved by +15 and in the horizontal direction and -15 in the y direction. And on top of that, also a medium filter was applied. So it's a little bit more blurry. That could be during the process that they can get some motion blur or something. And so we want to match these two images now. And looking at the brief descriptor, so that is a basic descriptor used. It finds 2 points, maybe not so perfect actually, but anyway, it finds 2 points here and here. Actually, I'm showing only 2 points. Looking at the matches we get with this brief descriptor, we see that one is clearly realistic. It has a very dark line. It's close. While the other one is less realistic. You can see here that it has a much less solid line. And the opacity is here is set by the inverse of the distance. Actually, a more realistic hit would be that it goes more between these items here, but it didn't manage that. Now going for the orb descriptor, which is a more complex algorithm to get these dots, we see that it finds very many more dots that are really good hits, and one exception which goes all across, but that can be rejected probably because it's not realistic. If all are going, or the majority are going in this direction, then yeah, then it's clear that it's not going to be realistic that all of a sudden one is going that direction. Then we can also compute average flow, and there are different ways to do this. The average flow can be computed spatially, temporally, or spatial temporally. The differences are, so that's just creating some data. It's a lot of loops to produce it. I'm not going into the details about it, but there is some motion in it. But spatial averaging is when you have only averaging in each time frame. It helps you because it makes you less noise sensitive in the frames. Another one, actually now we can see, oops, sorry, it wasn't meant to. No, wait. Oh, now I got lost. So, so computing the average flow, we can see, okay, we got a -1 flow in this data set that we had, which was the one moving before. But also we can make a more complicated flow, and you can see here we have image of some motions. You can see that the delta x motion here is -1 mostly, but there are some deviations, and we can see also in the y direction that it is also mainly going negative. And if we plot the motion field like this, then we can see also that everything is going consistently towards the lower corner of the image. Time averaging is when you average between the frames to see where it's moving. And that can also be shown. So we have also again here a lot of -1, -1s looking at this data. And doing the averaging, there is some scaling factor in here. So it's actually a 0.05 motion. So it's very small steps. So this plot actually doesn't show it very nicely. But in principle, we are doing a -1, -1 direction movement in this one too. The big one is if you actually add both filtering in within the frames and between the frames, and then you get a more robust average movement within these images. And here we have a little example where things are moving around all the time. You can see here that the tracks are changing depending on which time frame we are in. And this is more or less what we wanted to study. It's a very simple example here now. So that needs to be extracted to something more complicated when we really do it. Now, I hope my slides now actually come out well, because I had some problems in computing these. But yeah, that was the problem. Let's see. No. But in principle, when we have more complicated frames, it's not so easy to do the averaging or do the tracking at all. And then it gets more confusing how to work with the data. And that is something we have to really solve. We can have different problems when we do the tracking. So we can have random appearance, disappearance. So if you do imaging over a limited field or depth of field, it can be that some objects are actually going out beyond the borders of the image, and then they come back again. And finding them is maybe not so easy. So it could be that it actually appears as a new object when it comes back in. Also, segmentation can be a problem, that you, in some images, can't really segment the correct items or the really tracking points. And also, if you have motion artifacts, maybe your items are moving faster than you can really do. Then you will get some like comet tails behind them. And that is, they will have also lower intensity than objects that are standing still. Another thing is, let's see if I get that. No, okay. Another thing is also if you have objects that are splitting during the process or merging during the process. So think about, for example, a bubble study where you have bubbles that at some point they merge into several bubbles are going into one single, or for some reason they are splitting up into smaller bubbles. That is always things that you have to look into when you try to track objects. The jitter and motion noise is something that also can happen. The jitter is essentially something that is vibrating with some random magnitude and angle. So it's a kind of a random walk effect around the point where it should be. But also motion noise is something that can be a problem. Also, that would be that if you move some object, it may be not perfect in a straight line, because there is this jitter or motion noise. Limitations on tracking is we have a lot of parameters to play with. There are different from the experiment point of view. So flow rate, which kind of flow we are talking about, density of particles, how much objects come in and out of the image, and of course the jitter. Another thing is also particle uniqueness, which can be a problem. So if you have objects of the same type, like particles in an airflow tunnel where you just want to see how they move around and the object, then if you have the same object type, then it's more difficult to actually identify which one is which one is the same one. And that can be a little bit strange tracking if you don't get it right. So how we can improve the tracking is, of course, changing the sample rate to get more frames. If you have more frames, objects that was far away before, they get closer and closer because you have shorter time between the acquisitions. And another thing is also looking into the resolution. If we have many items, we may have to look for a different resolution to be able to resolve them. If you have small items in particular. And other parameters you can play with in the experiment, let's see, is also controlling the process by changing flow rate or type, also looking at particle uniqueness to avoid the problem that you have all the same object. Vibration or temperature changes will introduce the jitter, which we don't maybe also want. And also which kind of mixture we have between different objects in the sample, or what kind of densities we have available within this object. So we can also, here we can start doing some kind of simulation and see what can we actually capture with our tracking. So here is an example of a flow simulation. And we produce some different flow tracks here of different objects. And afterwards, we want to track these. This is probably a relatively simple one, but you can see there is some jitter introduced. We have a motion vector, which is going in upwards direction, but there is a little bit of jitter in the angle, so in the direction of it. And with this kind of simulation, we can see how well we can follow objects before we start doing the real data analysis. If we can't do it on this data, there is no chance we can do it with the real data. Designing experiments, you have to always control. I always mentioned, I have already mentioned many things, but you can always control. If you have a controlled experiment, you can check that you have the right concentration of some of the substances. But you can also play with the field of view, maybe, but depends on the camera system what it can do. You can also play with the frame flow per frame. So it's actually how much do the objects move from frame to frame. And that is actually a little bit of balance between what a frame rated camera can do and how much you can control the process. And of course, you can also check what jitter will have depending on the temperature conditions or something else, mechanical conditions in the system. Then is a question how much you need to capture. So if you have a 5% error in the bubble position, that would be maybe less than 5% of the flow field, but possibly more than 20% of error in the topology. So you have to check here exactly what parameters you really which parameters you really are interested in. 5% error in shape or volume can also give you 5%, directly 5% in distribution or changes in the distribution here. And usually it's more than 5% in some of the bubbles, individual changes. But it can also give you a really great change in the bubble strain tensor calculations. So you have to be careful about seeing where these errors are propagating into the parameters you want to measure. Now, there was a little discussion in the chat before the break, how you can improve the tracking. And there are a couple of things we can do. One is called the bijective requirement. And that is, in principle, you track and find an object from one frame to the other. And then you do the back checking, taking the original image and finding the best fit in that one. So you do here, you do from image, this is from image 0, checking with the pixels in image 1. And here you got this point, and then you compare that point to all the points in image 0. And if those two are the same, then you can say, great, this is a good tracking. Another thing you can also check is the maximum displacement. There are some positions that are not physically realistic. So for example, if you think back on the images I showed before with the brief, that there was one that was moving a short distance and one that was going across the whole image. Then you can say that, okay, it's not realistic that it moves this far between two images. You can also add more some other physical requirements also on direction. Can it at all move backwards or forwards or whatever? So you can add a lot of constraints when you do this tracking. You can also add priors. You can say that, so predicting what should be the next position. So you can, from the trajectory, let's see, I have my pen here. If you do a tracking, hello? No, it's not connected. Sorry. Sorry for that interruption. It should be working now, I hope. Yeah, now it works. Okay, so if you have some points going somehow, then you can say that based on this trajectory, you should be somewhere in this area for the next one. And then you should look for the next one over here, but that's pretty far away. So maybe you need a couple of points in order to be able to really track with the expected moment. So you can also use, so in principle, this is how the tracking is working, and there are many different models how to do this. This is essentially just a predicted offset that you expect them to move this far. Another one would be to look at what I said here, some kind of average motion going through the trajectory history. And of course, you can put in more physics into it. You can look at derivatives of how it's moving. And of course, you can also then going for the big gun using Kalman filters, which also models the jitter and noise uncertainties in this prediction. So the more certain you are, the the closer you get with this circle and when you search for the next one. So then you can also decide how big is this search area. So this is a pretty nice way of actually improving the quality of the tracking. Well, then we can also go beyond the nearest neighbor. So we can use, it's a good starting tool. So it's an easy thing to implement, but it may not be sufficient if you have more complicated flows with crossing trajectories and in the data set. So you can use some multiple hypothesis testing to work with it. Then you can explore what happens. How to look at different possibilities of trajectories and see which one is more probable. So the problem is also always that you have these merging and splitting particles, and that is something that is actually in the literature also a topic that people are looking into. You can also look into, let's just a moment. So voxel-based approaches. So now we are actually going away from actually characterizing single objects, but now we are looking at correlation instead. And with correlation, if you have two images and want to compare them, correlation would give you a point with the offset, how much it has moved. And you can do correlation in the real space. Then you have to do a lot of summing for each position, or you can do it in Fourier space. And the correlation in Fourier space is that you compute the Fourier transform of the first image, multiplied by the complex conjugate of the Fourier transform of the second image, and then do the inverse transform. So these are the two approaches. And here we have an image. So we have the 5 from the MNIST data set, and it's shifted by -3 and 2. And this one, it didn't want to run. No, okay. My computer doesn't like this today, it appears. I had it running yesterday. But anyway, this produces, in principle, how you do the summing, where you have the 5, the fixed image, and then you move and computing the sum across the whole image. And that gives you a peak where it's a good fit. You can also look at different metrics. So you can look at the mean squared error, you can look at the root mean square error, and looking for the minima. And this one is also one that didn't, but this one must run. Oh, this is a pity. Just a moment. I just need to restart things here. This was a tough one. Now it comes. Good. I just need to go back. I think I need. Oh, where is it now? That one here. So we got that one, and get that one running. I hope this takes a little time to execute, but I want to show it anyway. Let's hope it works now. Yeah. Yeah, you can see here that correlation in real space is something that takes time, even for a small image. Yeah, there it comes. Yay. Good. So here you can now see, so it's computing the difference between those two images, and you can see that there is a spot here, which is a good hit. And that should correspond to the position where we have the displacement we are asking for. So this is the process that's going on. And then we can also look at the Fourier transform. And you can see that we have the two images. The Fourier transform looks at the absolute value of the Fourier transform looks the same. The differences lie in the phase image. And if we do the multiplication again, so if we multiply by the complex conjugate and do the inverse Fourier transform, we can see that, yeah, we got a spot here, which is the -3 and +3 and -2, which is actually the displacement between the two images. So this works pretty fine for small regions. And when you do the tracking, or also if you want to do registration, this could be a way to do the fitting between the two images. Let's see. Yeah. So here we have a piece of the bone slice, and it has been displaced. You can see this characteristic feature here, which has moved a little bit up and sideways. And this one we want to now to correlate with the register. And the registration, I actually didn't mention that, is when you have two images and you want to have them on the same coordinate system, because otherwise you can't really do a real tracking. Then you can actually, the registration is about finding the point where the two images actually are on the same spot. And the reason why you need to do it is that your experiment may move around while the process is going on. It could be some instability. It could also be that the sample itself, by the process, is kind of changing a little bit shape. And then you want to have all images aligned along one row in the same coordinate system. This is something that's also very much related to the next week's lecture, which is about bimodal imaging or multimodal imaging. But also, if you have experiments where you may have taken in and out the sample, and the repeatability of the in and out operation may be not so precise as you would wish. I mean, in some cases, we are talking about microscopic measurements, and then you have to reposition exactly on the microscopic scale too. And that may be a bit tricky. So that is what you need to do for, as a registration is a process of matching the two images. Let's look a little bit smaller region. Should also work, I hope. Yep. And here we can see that they're actually a little bit quite shift from each other. So it's hard to actually identify which region belongs to what. And then we want to correlate these two or register these two. Sorry for these delays. Now is something that is also taking a little bit time to do. What is going on now is the registration of two images. And yeah, there we have it. Actually, what takes time is the visualization making this. It's the process itself doesn't take so long time, but rendering these movies takes some time. And then you can see here now how these images fit. And at some point, there is a strong minimum or maximum that we can use for repositioning the object. I'm actually skipping this one to save some time. So here you can see for example, in medical imaging, you have a patient which goes into the X-ray multiple times. And we want to have this patient anatomy aligned between the measurements. And you can see that's right now it's not so easy. Other thing is there are a lot of tubes and cables attached to the patient, not always on the same places. So that also can be confusing for the registration process. So that's something we need to watch out for. The process of doing this is we need to have one moving image and one fixed image. And the fixed one is also called reference image. Algorithmically, what components we need are, first of all, some kind of transform operation. That could be, the basic one would be just translations and rotations, but it could also be some skewing operation. Then we need some interpolator to do the resampling back into the right positions. And we need a metric to compare how good we are right now. And finally, there is also need for an optimizer, one that follows the metric and tells us now we have we are getting closer to the good fit now. So these are the components that we need. And if I'm lucky now, it should work. Yes, it worked. Good. So here we can see a graph, how we could work, for example. The basic thing is we have these components and we do some image. We have an image which is transformed and moved around with the interpolator, and then it's compared with the fixed image to get some metric. That could be least square, for example, or mean squared error or something like that. But there are also other metrics that people are using. And the full, let's see, yep, the full algorithm is then also including the optimizer. So it has been a little bit reshuffled here. But in principle, the new thing is that the metric is connected to an optimizer, which gives us the new transform coordinates, which goes back and then it iterates until the metric reaches a desired minimum or stabilizes. So this would be the standard algorithm for a registration. So yeah, we have already talked about the fixed and moving images. And also the transformation part, we have the affine, translation, scaling. Also deformable is a tricky one because then we're going from the rigid grid until something that is changing. So for example, if you have an, I don't know, an organ that is moving around or a piece of bread, which is going up while during the levitation process, that you can see as a deformable process. And shearing was when it's the interpolator. We have different kinds depending on how much time you want to spend on it. Nearest neighbor is a pretty simple one, but then bilinear or bicubic is probably the most used ones. And if you want to really do it exact, then you can also use the B-spline interpolation. Metric, we have different metrics here. I already mentioned the mean squared error, but that can be misleading. And there are some people claiming the structural similarity metric as one, or we can also look at correlation factors. And why not use a combination of them and put all into the optimizer and seeing where it's going to be best. The optimizer, many algorithms available. Very popular to start with is the gradient descent. One that has been developed in machine learning context is one called Adam, which is much more efficient than the gradient descent. It's used in many training of neural networks. Also, the stochastic gradient is the same. All these are algorithms that you can find, for example, in packages like TensorFlow. And for time reasons, I can't show you these examples, but there are some examples that need some actually also adjustments using TensorFlow in the notebook, but I'm skipping those slides because time is running up now. That was essentially the tracker we looked at before. So we have this kind of optimization. We have some kind of grid search going through the transform, doing a nearest neighbor interpolation, and checking that with mean squared error. So that could be an approach to work with. We have these two images. We want to register them. And one thing would be to look at these images as we just had them. No, I lost it. But this is a very binary image already in grayscale. So we have either background or holes. And if we segment that, we can see also, yeah, that's not so much difference. And the mean squared error may have problems of really finding a good match. So what we can do instead is we do this segmentation, thresholding it. It's probably not so important exactly how or how good, but the important thing is then we compute the distance map, and then we get much greater variations within the image, and that makes it much easier for the tracking to find the right spots. And so it's like if you have some kind of it's easier to find from a smooth surface than getting just discrete things, which would be maybe also misleading in the error calculation. So this is a way to get around with the registration. This I don't no. This is now the TensorFlow stuff that should actually have been skipped. Okay, another way. So the TensorFlow example is more for demonstration, but what mostly is used is the ITK or simple ITK toolboxes, which has a great collection of different algorithms for registration. There is even the further development called elastics or simple elastics, which is also used for the registration. And these are the currently toolboxes that are popular to use for the registration. Doing it is, as you can see here, a lot of code. So you can never get around writing code. If you are doing a registration with your own code, you have to write quite many lines. But in principle, you have to set which images. You have to set a transform, initialize it, and then go on with some optimizer to do this process. There are also tools to do this. Some are actually based on ITK. One is 3D Slicer, which has the ITK registration tools available with a nice user interface. So you can even set different constraints. You can mark points, fiducial points, to make the registration easier. So the first, I would just say, if you want to do registration, never done it before, it's probably better to use some GUI-based software to get first an idea how to work with it before you start writing your own code. Here, I didn't execute that one, but we have the images anyway. So here, it actually looks like it didn't do pretty well this time. So that's actually confusing. But in principle, what I would expect it to do is that it should find the two images pretty well, but apparently it didn't work that fine. Then you can also look into smaller blocks and do more correlation. on it. And actually now we are going into a new topic, which is digital volume correlation. Sorry. Look at smaller regions. And of course, you have smaller statistics in a box, but with that, you can start looking at local displacement in the image. And with that, we can start introducing physics, looking at strain vectors and deformation terms in our work. And that can be used then actually to really relate changes within the images, where you can see strain field showing how much is the local displacement. Of course, to do this, you have to divide. So if you have some image of something where you have, for example, a screw included, and then you pull the screw, and then you have two images like this, and you can see afterwards that you have a displacement field around this screw that you have been pulling. And this is the information you want to see, and you can also see how it evolves over time. This was what I'm sketching at here is work by a user we had who were working about metal implants or metal screws in bones. And they wanted to see how the displacement is. That was done with neutrons, but I think they also did some experiments using X-rays. But the problem with X-rays and metal is that you have a lot of metal artifacts, which makes it harder to see what's happening close to the screw. Then you can also look at different distributions, what different metrics over time. So things you can look at is, for example, the texture tensor. Let's see, we can maybe split this up a little bit. No? So we can look at this. So, and let's see. So now it's a little bit easier to look at it. So the texture tensor is something that is similar to what's it called? Structure tensor, but it's actually looking at different objects, how they are related to each other, and that can be used also for seeing how things are distributed over time. All we have to do, usually we have to define which metrics we have to want to look at, but this is one of them. Yeah, sorry for a little bit confusing description here. Another thing we can look at is the strain. So that's actually delta distance over distance. And in 1D, it's pretty easy, but in 2D or 3D, that can be a very difficult thing to measure. But with the help of digital volume correlation, we can actually get this information. And there are people working with it who actually include a lot of physics in the models nowadays, and can really see very small changes and see crack forming and seeing how the strain is moving around. If you're interested in this, I can dig out some publications, but I don't think I have it available right here now. But if anyone is interested in looking at digital volume correlation and strains, then there is a big literature out there. I think even there is a book I can pick up. So we have different types of strain to look at. So the total strain we have is, for one, the volumetric strain. So how things are changing in size or scale. And then we also have the deviatoric scale strain. So how different pieces are moving around in the object. So it's a kind of anisotropy changing within the object. And this brings me to the end of the lecture, and actually 11 o'clock. We have been talking about how to work and plan with dynamic experiments and how to do imaging with it and to get the best information from it. Then object tracking and registration are big topics when you do dynamic experiments. And finally, also some words about digital volume correlation and how you can use that to compute strain fields in images. And well, that was all for today. And yeah, well, I'm stopping the recording.